Gibbs sampling is a widely used Markov chain Monte Carlo method for multidimensional distributions. So in addition to being a popular technique, Gibbs sampling is also highly flexible, as we'll see. It's widely used for multidimensional distributions. It is the go-to method for Markov chain Monte Carlo for multiple dimensions. So let's suppose that our target distribution, the distribution that we want to describe using our sampling method, is again represented by P of x, where x is a vector, and this vector has components x1 through xm. We're also going to use this target distribution as the proposal distribution, and this is perhaps the biggest change to standard Markov chain Monte Carlo. So let's initialize a vector in this space, and we'll again call it x tau. So this is our starting point. So Gibbs sampling works by replacing one of the variables, let's say xi, from this vector set of variables x1 through xm. We're just going to take one of those variables xi, and we're going to draw from a now univariate distribution with that variable removed. So we take xi, we now say, what's the probability or the density for xi given all the other variables fixed? So we're only sampling across one dimension in that m-dimensional space. So we're moving effectively perpendicular in a perpendicular fashion through this multidimensional space, sampling just across one dimension at a time. And we cycle through the variables, so we go x1 through xm, or we can select randomly, just grab, let's say, x2, then x5, so forth. So you can do either one. Most Gibbs sampling methods do a cycle. They just roll through the variables in turn. But there are some, and in fact you can, in some Gibbs sampling algorithms, choose between a cycle or a random selection. More formally, the algorithm looks like this. We initialize with some point in this vector space. We'll call that x. And then for t, which indexes our iterations, and that goes from 1 to capital T, and for m that indexes our dimensions, and that goes from 1 to capital M, then we're going to sample a point in one of the dimensions, little m, at a time in the iteration count t, according to a draw from this target and proposal distribution, p, for one of the dimensions, xm, okay? And we're cycling, so we're going through them 1, 2, 3, all the way up to capital M. So we're at this particular point, and we're looking at xm, and that means that we're sampling from xm conditioned on all the other points, x1 through x minus m, and xm plus 1 to xm, so all those other dimensions. But notice that the ones x1 through xm minus 1 we've already sampled during this iteration, so we've still got the same iteration count t, whereas the ones that are beyond m, m plus 1 through m, we haven't yet sampled. So they're still at their previous point from the previous iteration, t minus 1. And that's how this works. We just go through each one of the dimensions one at a time in order and sample from one of those dimensions, fixing the other dimensions according to whether we've already seen them in this iteration or whether we saw them in the last iteration. So when we sample from this conditional distribution for one of these dimensions, one of these variables, xi, given all the others, okay, the distribution is invariant. This distribution with the one dimension removed is invariant. The joint distribution is invariant. And since these points don't change, they're fixed. This means that this Gibbs distribution, the P of x for all the points, for every point in the sample space, for every point in our vector space, for this random vector, is invariant for each of the Gibbs sampling steps. And also, each one of these steps samples from this conditional distribution that we pointed out, the conditional distribution of the one component of that vector, that random vector, that's been pulled out and everyone else left. And that combined with this marginal of the joint being invariant gives us the correct joint distribution for P of x. So this, in fact, is, our invariant Markov chain results will apply in that it will converge to the invariant values for that Markov chain, which will, in fact, be the target distribution, the correct values of the target distribution. And in this sense, Gibbs sampling is a special case of Metropolis Hastings where the acceptance is assured, and as we pointed out, we're using the proposal distribution as the same as the target distribution. So let's look at an example. And we can see by this example that the search through this space, in this particular case, we represented it by a contour of a multivariate or a bivariate Gaussian. We can see that our search is very similar to what we had in Metropolis Hastings. The only difference is that instead of going out in any direction from our target point or from our starting point, we in fact move in the directions of the axes of this distribution. And we always will move through one axis, then we'll move perpendicular, then we'll move that starting axis again and move perpendicular again, and so forth. So we're always moving along the axes. We never move across the entire space. This somewhat limits our search, but because we are in fact searching across all points in each of those spaces, we will cover the entire distribution and we will find what we're looking for, which is a good representation for the probability distribution that is our target. So as we pointed out, this is used for multidimensional problems, and it is used extensively for multidimensional Bayesian models when the conditions are met that we can use the target distribution as a proposal distribution. There's also something called blocking Gibbs sampling. There are a number of extensions to Gibbs sampling. This is perhaps one of the more common ones. And instead of doing one variable at a time, you can actually draw samples from sets of variables and proceed that way, which makes it a little faster. The usefulness of Gibbs sampling clearly depends on the ease of sampling from the proposal distribution. And that's the key feature that needs to be satisfied for Gibbs sampling to work well.